Okay, let us further continue on this course, microprocessors. What we have discussed in the previous class is that how the microprocessor basically executes a program or instructions. Okay, so you have a processor and you have memory. So you interface the memory with this microprocessor, and you have different buses for this. One is address bus, then we have the data bus, and then we have the control bus, which are single, you can say, lines for carrying the information between microprocessor and the memory. Okay, so memory, in the memory you can store the information, whether it is a program or whether it is a data, and each memory has a unique address. Okay, so that location, a particular location in a memory, is identified by basically a particular address. Okay, so this address is unique. So we have said that, okay, if you have 16 bits for address, so you can locate 64 KB. Okay, so 64 KB of memory you can attach with the processor. This much locations you can address, right? And each location can store 8 bit of data. It may be 16 bit of data also, that does not matter. Okay, so once you have written some program in the memory or some instruction in the memory, so then there is a sequence of which the processor follows, which we call as fetch, decode, and execute. Okay, these are three cycles in the instruction cycle. So the processor will first fetch the instruction from memory. It will give it to instruction decoder, which comes to know which operation has to be done, and then there is a ready-made circuit that gets activated, and the instruction is executed. Okay, so we explained this in detail in the last class. Okay. Now the question is that how you put the program or the data in the memory. Okay, so how you read or write the data, that we have discussed in the class. Okay, if you want to write some data into the memory, so what we do, we place the address of this location on the address bus. That location gets identified, then you place the data on the data bus and you activate a read write signal. Okay, so that data gets inside that memory. And if you want to get some information from the memory, or you want to read some data from the memory, so again you have to first place the address on the address bus to locate that location. Then the processor will send a control signal, which is read, and whatever data is placed on that location, that gets loaded on that data bus and it gets inside this processor. Now how you store this instruction and the data in the memory of this memory of the microcomputer. Okay, so since all the instructions and the data whatever you have, they are the binary numbers. Okay, so whether you have data or whether it is an instruction, it has to be stored in a binary format, because it is the only language that the processor can understand, which is called machine language. Okay, so like we have said that, okay, if you have an 8-bit processor, so you can have 2 to the power 8 or 256 different bit patterns. Okay, so each bit pattern has been used for a particular task or operation, that is called as operation code. So you have a 8-bit opcode for each instruction. So maybe suppose 10010001. So this is used for a particular application, supposed to add two numbers or to increment the data in the accumulator or whatever it is. So this is decided by the designers. Okay, this is what is called as the set of all these opcodes is called as the machine language, the language which the processor understands. Okay, so the set of all these instructions is called as the machine language of this processor. Okay, and this machine language varies from processor to processor. Okay, so Intel processors, they have different machine codes. Your Motorola or Zilog or some other manufacturers, so they have different machine codes. Okay, so that designer has decided that, okay, which bit pattern has to be used for which operation. Okay, this is what is done in the microprogramming. Now since we cannot write a program in this binary because it is very tedious for humans to do this programming in the binary. So we have developed, people have developed some separate, you can say easy or English like languages which are used for programming, and then those programs, they are converted into the machine language by a specific software or a program again. Okay, so first thing is that if you see the data manuals or the user manual of the processors, you will get the machine codes not in the binary form, they are basically in the hexadecimal form. Okay, so each machine code has a unique hexacode. Suppose you have an instruction, and that instruction is to add two numbers in A and B, and you have a machine code for that, and that is suppose 0 1 0 1 1 1 1 1. Okay, but if you see the user manual or the data sheet of the processor, you will not get this machine code, you will get its equivalent hexadecimal code. So it is 1 2 4, it is 5 FH. Okay, similarly for all these opcodes, for all the opcodes that are available which define the instruction set or this machine language of the processor, so you have a unique hexadecimal code which is given by the manufacturer in the datasheet. Okay, now how you convert, how this hexadecimal codes gets converted into this binary code, because see whatever you have to load in this memory, that must be a sequence of zeros and ones. The processor does not understand what is 5fh. Okay, it is just for our convenience. And say why we have introduced this hexadecimal number system when we already have this decibel numbers. Okay, we basically in our day-to-day life or real world we use decimal numbers. Okay, 0 1 2 up to 9, so you have 10 digits. It's called as base 10 system. Okay, so then what was the need to create this hexadecimal number system? Because see when you now see convert these decimal numbers into the binary format, because what we have to load inside the processor is a binary code. Okay, inside the memory. So to represent these digits from 0 to 9, we need a 4-bit code. Okay, because if you just 2-bit codes or 1-bit code, if you use, you can just represent 0 and 1, two numbers. Okay, if you use a 2-bit code, so you can have 4 numbers, 0 0 0 1 1 0 1 1. So the first 4 digits of the decimal number system 0 1 2 3, they can be represented by 2-bit code. Similarly, if you use a 3-bit code, you can go from 0 to 7. Okay, so to cover all these single digit decimal numbers, you need at least a 4-bit code. Okay, so 0 will be represented by 0 0 0, 0 0 0 1 2, and 9 is 1 0 0 1. Okay, so I hope that you have gone through this in the digital electronic circuits. 1 2 4 8, so 8 plus 1, that is 9. Okay, so it is 1 0 0 1. Now since we are using a 4-bit code, okay, but using the 4 bits you can have 16 possible combinations. Okay, so but if you refer to the decimal number systems, we are just using the 10 combinations for the digits from 0 to 9. So the rest of the 6 combinations, they are unused basically. Okay, so then people realize that okay, we should have a different number system in which all these 16 possible combinations, they are assigned a unique single digit code, right? So then this hexadecimal system can. Okay, now after 9, when you say 10, that is 8 plus 2, it means 1 0 1 0. Similarly 11, 1 0 1 1 up to 15, 1 1 1 1. So this was assigned a code A's, B, C, D, E, and F. So A is for 10 in decimal, B is for 11 in decimal, and up to F. Okay, so it gives a more compact representation or compressed form of the binary numbers, of course. Okay, so the advantage of this is that if you Say in the decimal number system, if you use a single digit number, you using a single digit number, you can have only 9 values, 0 to 9, of course 10. Okay, but if you have a decimal hexadecimal number systems using a single digit, it can go up to f, 0 to f. So it can go from 0 to 16, 0 to 15, of course 16 numbers you can represent using single digits. Okay, so the representation is more higher. Similarly, if you say a 2-digit number in decimal, so you can have maximum number is 2 digits 99, so you can have only 100 values. If you have hexadecimal number system, so using a 2-digit number, so if you use FF, it is 256. So you can represent 256 combinations using a 2-digit number in hexadecimal. Okay, so this is why we use hexadecimal codes basically, generally. Okay, to give a more compact representation of the binary codes. So all the manufacturers, they provide the equivalent hexadecimal code for the each machine code or the each operation code or code you say. Okay. Now the question is that how these hexadecimal codes they are turned into the machine codes. Okay. Let us suppose we have a simple program for addition of two numbers, and you have machine code for that. It may be 00000010. Okay, this is your opcode. What has to be stored in the memory is this. Okay, what is provided by the datasheet or the manufacturer is your its equivalent hexadecimal code, so 0 to h. Okay, so when you write instructions or a program, so you look for what operations are to be done, and you write all these opcodes in a sequence, and then you have to store all these opcodes in the memory in a sequence one by one. Okay, so for that, now for corresponding operation code in this machine language, you have a hexadecimal code. So the next code may be 3fh, next code may be 25h, and so on. Okay, so these hexadecimal codes, and then see in most of these single board microcomputers, which you will see in the college laboratories that we used for performing experiments on the processors. So what is available in those boards? You have a processor, a memory, you will have a microprocessor, then a memory, of course input outputs. Output is generally a 7-segment LED display. Okay, and then you will have a keyboard, which is input device, which is basically hexadecimal keyboard. Okay, so this is input device. So this keyboard is designed specifically for these hexadecimal number systems. Okay, so you have all these keys now. You have 0, 1, 2 up to 9, and then you have keys from A to A, B, C, D, E, F, and then you have some special keys for entering the data or for executing the data, for seeing the results, outputs, and so on. Okay, so when you press any key on this, let us suppose you want to enter this data 3f in the memory. Okay, so what we have to first set from this keyboard is the starting address, that where you want to store the program in the memory. Okay, so the starting address has to be specified. So let us suppose the starting address I give 20,000h. Okay, so it means your memory location is identified from where we are going to start this program. Okay, so the first instruction that we will load, it will be stored at this location. Okay, and you have to now enter 0 2. Okay, so you press 0 and 2. When you press these two keys on this hexadecimal code, So what was basically inside this memory is its equivalent machine code. Okay, so there is a program which is basically already in the ROM of this memory, which is not altered, which is called as monitor program. Okay, so the purpose of this monitor program is to convert these hexadecimal codes into the corresponding binary codes, machine codes. Okay, or you can say it is simply hex to binary converter, right? So whatever now program we have written, so what has to be stored in this memory is a binary code or a pattern of zeros and ones, but what you enter from this keyboard is the hexadecimal number. So the monitor program converts those hexadecimal values into the binary values and they get stored in the memory. Okay, and once you have loaded the entire program or the instructions in the memory, so once you hit this execute button, so the processor will start executing the instructions from the very first location. So it will first go to this address, fetch this instruction, decode it, execute it, increment by one, go to the next location, fetch, decode, execute, and so on. Okay, so it is a sequential process. It will fetch and decode and execute the instructions in a sequence one by one. Now again the question is, do we write the programs in the hexadecimal? No, because it is again tedious for us to write the programs in the hexadecimal codes. Okay, although in this is what is called as manual assembly or hand assembly. Okay, so we write a program, then you see what are the equivalent hexadecimal codes, and then you convert those codes into the machine codes which you basically load in the memory. Okay, so people have devised, okay, this is very tedious process to write this programming in the hexadecimal and the binaries of the machine language. So they have designed new languages. One is called as assembly language. Okay, so in the assembly language we are using English like, you can say, words which gives some meaningful information about what instruction the processor has to do. Okay, it does not give the exact information, of course, but you can have an idea about what this instruction is supposed to do. Okay, so like suppose if I write an instruction in the assembly, it is INRA. So you can understand, you may have an idea about what this instruction means. It means it has to increment the contents of accumulator A. So whatever is the data in this register A, that will get incremented by 1. Okay, similarly you may have instruction add C. So add C means it will add the contents of register C with accumulator, and that result will be stored in the accumulator. Okay, similarly you can have move A comma B. So it is a data copy instructions. With the contents of B, they are transferred to A, or not transferred, in fact they are copied to A. The contents of B remains as it is. Okay, so it is a copy operation from source to destination, and the contents of source, they are not destroyed basically. Okay, so this such a language we call them as, these English like words we call them as mnemonics, and the set of all these mnemonics that formulates your assembly language. Okay, so it is more easy now, see, to write the program in the assembly as compared with the machine or the hexadecimal codes. Okay, so for every instruction, now see, for every instruction we have a opcode, right? So opcode is basically the operation code, which is a binary pattern. This is what understood by the microprocessor. This is the only which is understood by the processor, nothing else. Okay, and corresponding to now each opcode, what the manufacturer provides you is a hex code. So for this operation code, it has, suppose this hexadecimal code is 1248, so it is 9 1293H. Okay, and corresponding to this operation code, you have a mnemonic now in the assembly language. Okay, so this bit pattern or this machine code has a particular meaning that is already decided. So it may be, suppose this instruction is to move the contents of register B into register A. Okay, so this is machine language now. This is hexadecimal code, and this is the opcode or the binary code. Okay, so what is understood by the processor is this one only. So this is for our own purpose. We have created this language for our own easiness so that you can easily write a program. Okay, similarly this is also not understood by the processor. What the processor understands is only the operation code or the machine code, which is the binary code. Okay, now see then how you will convert this assembly code into a machine code, because it has to be converted. Okay, the machine code is the only format that the processor understands. It does not understand the mnemonics or the assembly language. So you must have some program to convert this assembly code into a machine code. So we use a program or software for that, which is called as assembler. Okay, so if you write a code in the editor and you save it as .asm, it is assembly code, and this assembler will now convert this assembly language program into a machine code. Okay, so who puts this machine code inside the memory is not you, it is the assembler who creates the machine code depending upon this what we have written in the instructions or what mnemonics we have basically used. Of course, if it is a hand or manual assembly, you are directly putting the code in the memory using a hexadecimal keyboard. But if you use a assembler, the assembler will generate the equivalent machine code or the object code or the binary code for this corresponding assembly language program. And then there is a problem with assembly language. Okay, that since assembly language, although it is good to write a program in assembly language, but it is again machine dependent language. Okay, because see the machine code or the operation codes, they are machine dependent. So this language is also machine dependent. It means if you have written a assembly program for one processor, so that cannot be, you can say, transferred to some other processors. Okay, according to the assembler must also be unique for each processor. So 8085 if you are using, so you have a separate assembler for that, which will convert that assembly program into a machine language. And then people have, you can say, invented new languages which we call as high level languages. Okay, the machine language and the assembly language, they are classified as low level languages. Okay, both machine and assembly language. So for high level languages, they are basically machine independent somehow. Okay, so you have C, C++, or Java, Basic, Fortran. So these languages, they are machine independent. It means if you have written a program in C, so that can be executed on 8085. It can be executed on any other processor also. Okay, this is what is the advantage of high level languages, but they need more space to store these instructions. So these machine assembly language, they are very compact in fact. Okay, so for systems where the program storage or the program is very small in size, so we try to prefer write a code in the assembly language, not in the high level language. But when the program is very large and you may need to debug it or troubleshoot the program at any time to find somewhere else, so you try to go for high level languages. Okay, or if for real time applications where you want that, you can say this efficiency of or the speed of operation of this assembly language, that is much faster as compared to high level languages. Okay, so for real time applications we try to go for assembly language as compared to the high level languages. Again, you need some software or a program to convert this program written in C to a machine code, because this language is not understood by the processor again. So we have a compiler for that. Okay. So compiler is a program. When you compile a program, it means you are converting that C program into a machine code. Okay, so that job is done by the compiler in case of high level in languages, which converts that high level, you can say, program which is written in the C or C++, so it is converted into the machine language. But if you use a assembly language, so you have a assembler which is used to convert that program into the machine code. So ultimately what is stored inside the processor is the machine code only, binary code. Okay, so hexadecimal codes, your assembly language, your high level languages, they are just for our convenience. Okay, our easiness. They are not understood by the processor. What the processor understands is only pattern of zeros and ones. Okay, so I hope I am clear in this. And now see, I will give you one example. We write a assembly program and how we execute it inside the processor. Okay, let us suppose I take very simple example. You have to add two numbers. One number is in register A and this number is suppose 02. One number is in register B, it is F2H. So you have to write a program to add the two numbers and store this data in accumulator register A. Okay, this is the problem formulation or objective, you can say. Now you have to start a program in the assembly language. Okay, so what I have to see first, I have to now go to the instruction manual of the processor that I'm using. Suppose I'm using 8085 processor, so I have to see the instruction set. Okay, and from those instruction set I have to look for the instructions which I want to use for this purpose, isn't it? So I have to see first that okay, I want to load the data into register A, then into B, and then I have to add them. So I need some information. I need instruction which will copy a data that is 02 into accumulator A. Okay, so I will see from the instruction set and I will get to know okay, there is an instruction for that which is called as MVI, move immediate A02. Okay, so this instruction copies a data into the register A, whatever data you supply here. Suppose I have data is 2, so I have written 2. Then I have to use one more instruction, MVI B comma F2H. This instruction will copy a data into register B, that is F2, and then I have to add them. So for that I have instruction add B. So this instruction will add the contents of A and B and will store the result in A. Okay, this is my assembly language program, and then to stop this program I use the instruction halt, HLT. Okay, whenever this microprocessor will read this instruction or fetch this instruction, it will stop executing the program. Okay, so this is my assembly language program. Now if you do a manual assembly or hand assembly, you have to convert this assembly program into a hexadecimal codes. Okay, for each instructions there are two things. One is the opcode, which is called as operation code, and one is called as operand. Okay, operand means the data. So opcode defines that which operation has to be performed, and operand means the data on which that operation has to be done. Okay, so you will look into the data sheet of this microprocessor and you will see that okay, for MVIA comma some data, that data can be anything. So this data can be anything. Okay, you can load in an 8-bit number here. So for this there is a separate machine code. Okay, or equivalently it will be hexadecimal code. Suppose you have a code for that, suppose it is 32H. It means whenever the processor will fetch this instruction, decode it, it will come to know that okay, it has to load the data into accumulator. Okay, and the data must be supplied now, which has to be loaded into accumulator A. Okay, so this is opcode. 32H now is the opcode, and what is data or operand? That is 02H. Okay, so to complete this instruction, you need two memory locations. One to store the opcode, that is 32H suppose, and the second is the data. So it is called as a 2-byte instruction. So you need two memory locations. Okay, first for the operation code, second for the operand. Similarly, MVI B comma F2H. So to load some data into the register B, there should be a separate opcode. Okay, and let's suppose that opcode is F2H. And then since the data you had that you want to upload in the processor is F2H, so next will be data F2H. Then add B. Now since then this has only opcode, it does not have any data because the data is already in the registers B and A. Data is implicit here. Okay, so this will be requiring only one memory location, and let us suppose it is 20H. Okay, and then halt it is suppose 76H. So this is the equivalent hexadecimal codes for this program now. Okay, so the first 2 bytes they are used for completion of this instruction. Next 2 memory locations they have the instructions and data for the next. The third is for addition, and last is for stopping the execution of program. Okay, now how the processor will work. First you have to load now this data in the memory. Okay, so if it is manual assembly, so you just type the starting address and write 32H. It will go at the first memory location. So wherever you start, so suppose you start from 20,000H, so you load here 32H, not 32H, in fact it's binary code, that is opcode. So you type 32H, but what is goes inside this memory is its binary equivalent, hexadecimal to binary conversion. Okay, and then you start next location, you store 2H, then F2H, then again F2H, then 20, then 76. Everything is in hexadecimal. Okay, so 32H, which is in hexadecimal, but its equivalent binary code is basically stored at this location. Then at next location you are storing the next code, and so on. Okay, now you have written the program or instructions inside this memory. Okay, so it can be done by the hand assembly or the manual assembly, or it may be done by the assembler which would convert the entire program into the machine code. Now how the processor will work. So once you execute it, the processor will first fetch this instruction. Okay, it will place the address on the address bus, and then it will send a read signal, and then this data 32H will be loaded on the data bus. It will come inside the processor. It will give in to the instruction decoder, and the instruction decoder will decode instruction, and the processor will come to know that okay, it has to load a data into accumulator register A. So it will ask for that data. Okay, so next that data 2 will be uploaded on the data bus, and it will go inside the microprocessor. Okay, in register A. Okay, so first it will fetch this opcode, operation code, which will identify the type of operation, that what has to be done. Okay, and in the next case it will ask, okay, it comes to know that it has to load accumulator A with some data. It means the next byte, that is not instruction, it is a data byte. So 02 will be taken as a data, and it will go inside A. Similarly, when the processor execute, now this instruction is complete. Okay, MVI A comma 02. So 02 is loaded into your accumulator. So when the processor now since this instruction is complete, now the next binary pattern that will take, it will take it as an instruction again. Okay, now when F2H is fetched, decoded, it comes to know that okay, it has to load a number B into a number F2H, or a number simply into register B. It means you have to supply that number. So the data at the next location F2H is now a data. It is a number, it is not basically a instruction. Okay, so see, this is what point I want to make. The processor does not understand whether it is an instruction or it is a data. Okay, F2H can be instruction also, F2H can be a data also. So how it is going to interpret whether it is an instruction or data? It is not going to interpret. It is you have to make the decision. Okay, it means the first time the processor, the first code that the processor fetches, it is always taken as an instruction, not as a data. Okay, so if it is 2 byte instruction, it means okay, this is the first byte is the instruction, the second is the data. Similarly, if this is a 2 byte instruction, it means the first one is the instruction, the second one is the data. Okay, so these two memory locations will hold this next instruction, so it is completed. And then since this instruction is completed, it is a 2 byte instruction, it means your next is again an instruction, so 20h. So 20h, it will come to know it has to add the two numbers b and a and put the result in a. So it will send a control signal or a clock signal to the address circuit, which is already in the ALU, and these two numbers will be added and stored in a. And then it comes to 76, the processor will come to know that it has to stop the execution of the program. Okay, it will stop there. If you write any instruction after the 76, they are not going to be executed by the processor. It will stop here only. Okay, this is what is a halt operation. So this is how the processor reads the instructions, executes them in a sequence. Okay, and the processor does not differentiate between the data and the instructions, mind it. Okay, so you can have some binary code, it may be 0 1 0 1 0 1 0 1. It can be opcode, this can be data as well. So whether it is a opcode or data, the processor will not differentiate. Okay, but say if I fetch this instruction first, it means the first instruction that it will fetch, it is always the instruction. It is not, it cannot be data. Okay, now if that instruction is 1 byte instruction, it is computed in a single shot. If that instruction is a 2 byte instruction, it means you need one more byte to supply, which supplies basically the data for the instruction. So that will be in the next memory location, and so on. So similarly, we have some instructions which are 3 byte also. So first byte is the opcode, and mostly the next 2 bytes they carry the address of some memory locations. Okay, so we will come to that at a later stage when we discuss the instructions in detail. But this is what is the general how you write a program in the assembly. So for every processor, so for every microprocessor, you have an instruction set. Okay, which is a set of mnemonics, and these contains English like words move, a, b, increment, decrement, maybe. Okay, add, subtract, so on. So this set of instructions is called as instruction set, or the assembly. This forms the assembly language. Now, corresponding to each mnemonics, you have a hexadecimal code. Okay, which is the equivalent, which is basically the equivalent code of the corresponding the machine code, which is understood by the processor. Okay, so every instruction has a unique hexadecimal code. So it may be 20H for some, it may be 33FH, 49H, and so on. Okay, and then you have machine code. Okay, so machine code is the binary equivalent of this hexadecimal. So if it is 20, it means it is 0010 0000. So this is what is understood by the processor. This is not understood, this is not understood. These we have created for our own easiness. Okay, so whenever you write a program now for my microprocessor, whatever operation you want to do, so you have to first see what is the instruction set, because that instruction set gives an idea that what are the operations that are available that the processor can do. That gives a capability of the processor. See, in most of the processors like in 8085, you do not have instruction for multiply and divide. Okay, if you go to 8086, there is an instruction for multiply. Okay, it means if you want to do some multiply operations, so in 8086 that can be done using a single instructions. But if you use 8085, so since no single instruction for multiplication, It means you have to use a method of repeated addition. Okay, so you have to implement now multiplication using addition, so that will take more time. Okay, that is what is the meaning of this instruction set. So every processor has a fixed instruction set. Okay, and that defines the capability or the computing power of that processor. So whenever you write a program for any processor, you have to just see the instruction set. Okay, these are the instructions available which the processor can perform. So you have to choose those instruction sets, and you have to arrange them in a sequence for a particular program. So once you have a set of instructions for a particular program, then you have to create its equivalent hexadecimal codes, and then these codes are to be converted into the machine codes using hexadecimal keyboard in a single board microcomputer. Otherwise, if you have an assembler, so just write a program in the assembler, and that will convert automatically this entire program into its equivalent machine code. Okay, so that machine code gets now burned inside this memory. Okay, and once you start executing, once the processor starts executing this program, so it will always start from the first instruction where you have started writing this program. Okay, and then it will sequentially fetch, decode, execute one instruction. Once this is complete, go to the next instruction, go to the next instruction, and so on. Okay, so the purpose of this processor is to execute programs or set of instructions basically. Okay, and those instructions are in the binary format or binary language, machine language, and those has to be stored in the memory before the processor can start and execution of those instructions. Okay, so we'll stop here, we will continue next. So I think these 2-3 lectures I have taken about a general introduction about this course. What is the processor, what is the controller, how the processor works, what is the memory, how we interface in memory, how the read and write operations that takes place. Okay, what is the machine language, how it is different from the assembly language and these high level languages, and what is the assembler, and what is the compiler, and what are the advantages of machine language, sorry, this assembly language over these high level languages. Okay, and the general architecture of this, you can say, microcomputer. We have processor in this which itself contains ALU registers and the control circuits. Then we have input and output devices. Okay, an important thing is that the processor controls all these devices, the memory as well as input output devices. So there is no direct connection between this memory and the input output. Everything has to be controlled by this processor. Okay.